Here is a quick recap of the Taylor series centered about x. Notice that for x minus h, every odd term is negative. Otherwise, it is identical to the expansion for x plus h. If you are not familiar with big O notation, check out the first part of this lesson for a brief explanation. This screen shows the detailed steps to expand x plus 2h. It could be a good reminder of basic algebra, like distributing the power to each term, multiplying fractions, and simplifying them. The final result is in the last line. Take a moment to pause the video and reflect for as long as you need. Similar to the previous screen, this shows detailed steps to expand x minus 2h. The primary difference is dealing with negative signs. Since these are common stumbling blocks among students, I've included this as another good reminder. As before, the final result is in the last line. We can write all these expansions as shown here. I've included the seemingly trivial statement that f of x is equal to f of x. It will become more clear later on why I have included this. One more quick note and we will return to this table. Remember the second order central difference formula from the first part of this lesson? We mentioned that higher order expressions produce approximations that are closer to the true value. However, we haven't yet discussed how to find those higher order expressions. In short, I can tell you the trick is to include more terms. Take a look at the fourth order approximation, denoted by the OH to the fourth. It has 4 terms, whereas the second order has only 2, f sub I plus 1 and f sub I minus 1. In the rest of this lesson, we will show why this works. Then, we will work to derive more general finite difference expressions. I have pulled the coefficients from the previous screen and multiplied them by each term in our Taylor series expansions. These are the fractions in parentheses, 1 over 12 and 2/3. Note that 2 over 3 is just 8 over 12 in lowest terms. Also remember from the first video that f of x minus 2h is just a different notation for f sub I minus 2, and likewise for the others. Not much has changed from the previous screen to this one, mostly just bookkeeping. Here I have multiplied the fractions and combined them into one number for each term. Feel free to pause the video at any point so you can take notes and follow along at your own pace. The only difference between this screen and the previous is distributing the minus signs. Now there is only addition between each term, no subtraction. This is important for the next step. Now I add the numbers in parentheses for each column and record my answer below the line. Notice that each term is 0 except for f prime. This is the first derivative, which is what we wanted to find. Of course, this expression is still fifth order, as denoted by the OH to the fifth, because we truncated each series expansion after the fourth derivative. The first line on this screen summarizes what we found in the last step. In the second line, I have simply found a common denominator for the fractions. Then I divided each term by h in the third line. Notice this has reduced our expression from fifth order to fourth order. In the last line, I basically swapped the left-hand side and right-hand side. So it can be seen that by adding multiple Taylor series expansions together, we can increase the order of our approximation. I've just shown this specifically for a fourth order central difference approximation to the first derivative. Here I have pulled the data from our first lesson on finite difference methods. We will plug it into our expression to approximate the derivative of sine at x equals 0.8 and then compare it to the exact value of cosine 0.8. This shows how I plugged in the numbers. Now pause the video. Refer back to the previous table. See where I pulled the numbers from, and plug them into your calculator to make sure you get the same answer I did. Notice that h equals 0.2, because that is the spacing we used. This is the data table for h equals 0.1, which also appeared in our first lesson on finite difference methods. Same drill as before. Pause the video. Refer back to the previous table to see where I pulled the numbers from, and plug them into your calculator to make sure you get the same answer I did. This time, h equals 0.1. Here I have summarized the data in a table. We already looked at the absolute error for second-order central difference. This time, let's look at the absolute error for fourth-order central difference. Remember, the exact value is the number highlighted in yellow at the top of the screen. First of all, the error is much smaller for fourth order than it is for second order. Also, if we reduce our spacing h by a factor of 2, from 0.2 to 0.1, the error is reduced by a factor of 16. This is because 2 to the fourth power equals 16. Hopefully by now you can see the utility of using higher order methods, as well as the benefit of a reduced spacing. However, one drawback to reduced spacing is an increased number of data points over the same range, which require more time to evaluate. Often in computer science, there is a tension to reduce computation time while simultaneously improving accuracy. So it is that a balance must be struck for the situation at hand. That's all the more I'll say on that topic for now, but I leave you to ponder the implications of that. Thank you so much for your attention today. I know there are a lot of details involved with this stuff, so please feel free to ask questions in the comment section below. Also, stick around for the next lesson. We are going to take what we saw today and generalize it. That will unlock the secret to finding any finite difference method we want.